Okay, so 10.6 is comparison tests for convergence. We're going to learn about two different comparison tests, the original and then the comparison test for limits. So the original comparison test says let 0 be less than a sub n be less than or equal to b sub n. This is very important when doing the comparison tests. Okay, remember a sub n is always going to be the part that it's attached to the summation. Okay, so it says if the summation of b sub n converges, then the summation of a sub n converges. Okay. And then the next one says if the summation of a sub n diverges, then the summation of b sub n diverges. Okay, this is only the case if a sub n is less than or equal to b sub n. Okay, bless you. So if a sub n is greater than b sub n, then these conditions do not apply. And that's the big idea here, is you need to make sure you pay attention to that part that I highlighted. Okay. So looking at number 1, we have the summation of 1 over 3 plus 2 to the n power. This entire thing here is a sub n. Okay, the comparison test, all it's talking about is if we can find some other series, okay, other b sub n, that is similar to the summation that we're looking at, okay, if we can prove that that series converges or diverges, then we can also imply that a sub n series converges or diverges. So the best way to do this is to look at our problem, our a sub n, and notice in here we can take out the function, so we're kind of ignoring that constant in the front, the 3 plus. Okay, we can say let's compare 1 over 2 to the n power. Okay, so it's almost like we are reducing it by getting rid of that constant. But again, take that term lightly because we're not actually reducing it. Okay. It's just that 1 over 2 to the n is easier to deal with without that plus 3 constant. So this is going to be our b sub n. So if we look at what we're trying to compare it to, notice that another way to write 1 over 2 to the n power is 1/2 to the n power, which looks like what type of series? Geometric. Okay. Okay, remember a geometric series, we look at the common ratio, r, and see if it is less than or greater than or equal to 1. So since our common ratio r is 1/2, and 1/2 is less than 1, we know that this is going to converge. And again, that is because we identified this as a geometric series. Okay. The next step we have to do is we have to look at a sub n and look at b sub n, and you have to be able to tell me which one is smaller. Okay, so looking at those two fractions, would a sub n be smaller or b sub n?
A sub n. Or a sub n.
A sub n. Why a sub n?
Because it has a higher denominator.
Good. Remember, if we have a larger denominator, that means the fraction is smaller. Okay, so that means a sub n is smaller than b sub n. So going back up to this inequality up here, notice how it matches that inequality. So I'm going to write that. I'm going to write 0 is less than 1 over 3 plus 2 to the n power, which is less than 1 over 2n. Again, this is a sub n is less than b sub n, which fits the condition. So because 1 over 2 to the n power converges, that means this function also, or sorry, this series also converges. Okay. The only thing you need to add is your justification. And so even though the side part where we're talking about geometric series does justify that comparison one, we have to still say that this entire problem is true due to the comparison tests. Okay. Any questions on 1? Okay, so this is also a good example of if you did not recognize that this was a geometric series, okay, then you would not have been able to come to this conclusion. Okay. Well, let's look at number 2. So number 2, again, we have the summation of this equation here. This is a sub n. Okay, we're going to compare this to what? Any ideas? 1 over 4n. Okay. Another way to write this is what?
1/4 to the n.
1/4 to the n power, which means this is what type of series? Good. So this is a geometric series. We know that geometric series means the absolute value of r, which is the common ratio, has to be less than 1. So 1/4 is less than 1. This tells us that this series is going to what? Converge. Okay, so now what we need to do, because this is our b sub n, and this is a sub n, we need to see, okay, which of these is smaller? A sub n or b sub n? Okay, a sub n. Okay. Wait, are you sure? B sub n is smaller. Why? Good, it's subtracting a number. Subtracting a number, right? The last one we were adding a number, that's why it was bigger. We were adding to 2 to the n power. Now we're subtracting from our comparison. Mm-hmm. Mm-hmm. So that means b sub n is smaller. If we go back up to our ratio up here, not ratio, sorry, inequality, remember b sub n has to be larger. So if I was to write this out, if I was to write the inequality, it would be 0 is less than 1 over 4n, which is less than 1 over 4n minus 3. So again, this is saying bn less than an, which doesn't work. Okay, so instead, we have to look back up at our comparison, our b sub n, and we need to pick something that is smaller than 1 over 4 to the n power.
1 over 5 to the n power.
Did I say that right? That's something that is larger. Sorry, larger. Because we want it to be, this is where it is right now. It is already smaller. We want this term to be in the middle because we're trying to see if it converges or diverges. So we need a term that is larger than 1 over 4n. Okay.
1 over 4 minus 4.
Sure, that could work. That could work. That's getting a little confusing there. But what about another geometric series, but instead of 1/4 as our r, we can make it 1/2. Okay, that works. Or 1/3 would also work as well. So we'll do 1/2. Okay, so again, we're going to compare. Now we're going to do 1/2. So this is 1/2 to the n power, which is the same as 1 over 2 to the power of n. Again, this is geometric. So based on everything we just talked about above, we know this is going to converge. Okay, so now when I write a sub n, my a sub n will be in the middle, which means that it is less than b sub n. So now I have 0 is less than 1 over 4 to the n minus 3, less than 1 over 2 to the n. And since 1 over 2 to the n converges, that means 1 over 4 to the power of n minus 3 converges. So we can say that this converges due to the comparison test. So with that in mind, with what we did on number 2, okay, that means instead of choosing the 1 over 4n the first time, if we already made the connection that it is not large enough, then we don't have to choose that 1 over 4n. We could have automatically just chose 1 over 2n. Okay, we don't have to keep choosing different comparison series to compare. But just since this is the start of the notes, I want to show everything. Yes?
So they're not. So we're just guessing what B of n is technically. Like they're not going to give us like an equation or anything.
Correct. Correct. And you're trying to choose a B sub n where you know how to see if it converges or diverges. So you wouldn't just pick a random type of series that you don't know how to prove convergence or divergence.
Okay.
It'd have to be one that you know. So that's why we keep picking also geometric ones, because we've learned about those.
Okay.
Okay, let's look at number 3. So notice on number 3, now looking at our A sub n, okay, would you say that this one is representing a geometric series? No, it's not representing a geometric series because we actually have a quadratic in the bottom, in the denominator. Okay, so really what I can compare this to, if I was to get rid of all of these coefficients and extra constants that don't really matter, I am left with just 1 over n squared. Okay, and 1 over n squared is what type of series? A p series, the one that we just learned in the previous notes, the p series. So this is the p series. Okay, and remember, the p series says that our p has to be positive. Is 2 positive? Yes. And since p, which is 2, is greater than 1, we know that this series is going to converge. Okay, so the next thing we need to do, since this is b sub n, is we need to make sure that our a sub n is smaller than b sub n. Yes or no? Yes. So we have 0 less than 1 over 7n squared plus 4 less than 1 over n squared. Again, this is a sub n less than b sub n, which is good. That's what we wanted. Which means since 1 over n squared converges, because it's a p series where p is greater than 1, then we know that this series in the middle is also going to converge due to comparison tests. You have to include that for your justification. Okay, so 1, 2, and 3 is a lot. Okay, it's a lot of, do you remember what these series are? Do you remember all the rules for convergence and divergence? And then you have to think to yourself, okay, which one is greater, which one is less than? Okay. The next comparison test that we're going to learn about is a lot easier because we do not care whether or not an is less than bn. So this is called the limit comparison test. It says as long as an and bn are positive, okay, as long as they're greater than 0, then we can take the limit as n approaches infinity of a sub n over b sub n. And as long as we get a limit that is finite, which means exists, and positive, then we can say that the summation of a sub n and the summation of b sub n either both converge or both diverge. Okay, so let's look at number 4. Okay, so in this summation, our first step to look at is notice that they already have our a sub n. This whole thing is a sub n. Okay, we need to find b sub n, which is going to be what we're comparing it to. And in order to figure out what we're comparing it to, we really just care about the highest degree on the numerator and the denominator. So the highest degree is attached to 2n squared on the top, and then it's attached to 5n to the fifth on the bottom. So if we were thinking of a comparison equation, we would take 2n squared over 5n to the fifth. Okay. For these comparison problems, we do not care about any coefficients, so I'm just going to cross off the coefficients. And then how can I reduce n squared over n to the fifth? So this would be 1 over n cubed. So this is going to be our comparison equation. Okay. Now, looking at that comparison, this is our b sub n. Okay, what type of series is it? A p-series. So this is a p-series where p is equal to 3. And since 3 is greater than 1, we know that this is going to converge. Okay. So what we do is we take the limit as n approaches infinity of a sub n, which is this entire thing here, and we divide it by b sub n. But instead of dividing by a fraction, that's the same as multiplying by its reciprocal. So I'm really multiplying by n cubed over 1. Okay. When I do that, I get the limit as n approaches infinity of 2n to the fifth power minus 2n cubed all over the denominator, which did not change. So if I plug in infinity, as all of these n values approaches infinity, notice that this part of both the numerator and the denominator is insignificant because they already have higher degrees, higher than 3 and 1. Okay, then we're left with 2n to the fifth power over 5n to the fifth power, which means I can do what with the n's? Cancel them, and that means I'm left with the answer of 2 over 5, which proves that this limit exists. Okay, and what was the other condition? It exists and it has to be positive. So since those conditions are met, then I'm able to say that this series converges by the limit comparison test. Okay, or due to the limit comparison test. You need that justification at the end. Okay, so really what we could have done, let's say this is multiple choice. You don't have to show anything. As long as you see that we know that this is going to compare to that p-series, and this p-value is greater than 1 and it's going to converge, really, if you just look at the leading coefficients, that is going to be your limit. Okay, and that's how you can easily go through this problem without, and I want to say, if it's multiple choice, of course, because you don't have to show work. Okay, if this was FRQ, you would have to show all the steps, just like we did on the problem in order to get points. But I'm just trying to show you here that this is where that 2/5 really came from. Because if we're just setting the entire series as n approaches infinity. Any questions on 4? Okay, let's look at 5. Okay, so remember our first step is to look at the highest degree on both numerator and denominator. Okay, there's nothing on the numerator, it's just a constant value. But on the denominator, I have 5n squared, which means I can compare this to 1 over, I don't really care about the 5, so this would just be 1 over n squared, which is what type of series? P series. And what is P? 2, and greater than 1 or between 0 and 1? Greater than 1, which means this series is going to converge. Okay, next step, I say the limit as n approaches infinity of the entire a sub n, so 1 over 5n squared plus 5n plus 5, divided by b sub n, but instead of dividing, I'm multiplying by the reciprocal, so this is n squared over 1. So I have the limit as n approaches infinity of n squared over 5n squared plus 5n plus 5. Again, as n is approaching infinity, the 5n and the 5 on the bottom are insignificant because n squared is already higher. It's already going to be increasing towards infinity faster. And so we're left with n squared over 5n squared. The n squareds cancel, and I'm left with the limit is equal to 1 over 5, which means it exists and 1/5 is positive, so it meets the conditions. So we can say that this series converges by the limit comparison test. Okay, let's look at 6. Okay, so number 6, we have the summation of 1 over the square root of 3n plus 2. So again, we look at the highest degree on the top and the bottom, and really we just have this square root of 3n. So if we're comparing it to something, we're going to end up comparing it to 1 over, we don't care about the coefficient. Good, n to the 1/2, because square root of n is the same as saying n to the 1/2. And you did this because it can be easily identified as what series? A p series, where p is equal to 1/2. And remember, if it is less than 1, but between 0 and 1, we say that this diverges. Okay, so that means I take the limit as n approaches infinity of a sub n, which is this entire part here, and multiply by the reciprocal of our comparison function, which I'm just going to write into the 1/2 as the square root of n. Okay. So then multiplying, I get limit as n approaches infinity of the square root of n over the square root of 3n plus 2. Okay, again, as this is approaching infinity, that plus 2 is insignificant. That can go away. Okay, and then we have the square root of n over, because this can be written as the square root of n over the square root of 3 times the square root of n. So the square root of n is now gone, and so our answer is 1 over square roots of 3. Is that positive? Yes, so that meets that condition, which means that this series diverges due to the limit comparison test. Okay, any questions so far? This one's a lot easier, I think, than the other one. Okay, number 7. Okay, number 7 again. First step is to look at the part that has the highest degree on top and bottom. So that's going to be n cubed and 2n to the 5th power. So for our comparison, we're looking at n cubed over 2n to the 5th. Okay, we don't care about coefficients in the front, so really this is just n cubed over n to the 5th, which can reduce to what? Good, 1 over n squared, which is what type of series? This is a p series with p equal to 2, and since that is greater than 1, this series converges. So then I do the limit as n approaches infinity of n cubed minus 7 over 2n to the 5th plus n squared plus n plus 1 times what? Good, n squared over 1. We multiply by the reciprocal, same as dividing by that fraction. So I have the limit as n approaches infinity of n to the 5th power minus 7n squared over 2n to the 5th power plus n squared plus n plus 1 we're looking at the limit as n approaches infinity, which means the negative 7n squared does not matter on the top because we have n to the fifth. And the n squared plus n plus 1 doesn't matter on the bottom because we have 2 n to the fifth. So if we're left with n to the fifth over 2 n to the fifth, what's going to happen with the n's? It's going to cancel, and we are left with 1/2, which again is positive, so it meets the condition. So then we say that this series converges due to the limit comparison test. Okay, let's look at number 8. Okay, so number 8 is different than all the other ones. Notice we have the summation of n times 3 to the n over 4n cubed plus 2. So we're still doing the same process. We're still looking to see what has the highest degree. So the numerator, we circle that entire thing. And then we look at 4n cubed. Okay, so we're comparing, our comparison function, our b sub n, is going to be n times 3 to the n power over 4n cubed. Okay, we can ignore the 4 that's in front of the n cubed. It's just a coefficient. And we can reduce the n over n cubed. And so this is 3n over, or sorry, 3 to the n power over n squared. Okay, so this is the comparison function we're going to use. Notice it is not a p-series, okay, because the numerator is not 1. And it's also not a geometric series. Okay, so if we can identify the series, then we need to go think of the other tests that we learned about. And one of those tests was the nth term test for divergence. So I'm going to write that. Okay, the nth term test for divergence. Okay, remember it states if we do the limit as n approaches infinity of 3 to the n power over n squared, and if it doesn't equal 0, then it diverges. Okay, well, right away we know that if we do infinity on both, okay, it's just going to be rapidly increasing on the numerator faster than the denominator. So it's just going to be equal to infinity. And since infinity is not equal to 0, we know that this series is going to diverge. Okay? Remember, the nth term test always is for divergence. Okay? So now that we figured out that our comparison diverges, we then set up our limit comparison test. So we do the limit as n approaches infinity of a sub n. Okay, so that is n times 3 to the power of n over 4n cubed plus 2. Okay, times the reciprocal. So that's n squared over 3n. Notice when we do that, what cancels? The 3 n's. Okay, and so I am left with n cubed over 4n cubed plus 2. Okay, I don't care about this plus 2. It's not going to do anything as n approaches infinity, which means I have n cubed over 4n cubed. So what's going to cancel next? N cubed. And so my answer to this limit is 1/4. Is this positive? Yes, so that means my comparison diverges. So this series of a sub n also has to diverge. So diverges by the limit comparison test. Okay, so this one was unlike the other ones. We could not automatically just assume p-series and had to use another test to see if it converge or diverge. Any questions so far? Okay, last problem. We have the summation of n over the square root of n cubed plus n. We circled the highest degree on both the numerator and the denominator. Okay, this becomes our comparison. So compare, we have n over the square root of n cubed. How would we write that in terms of exponents?
3 over 2.
3 over 2. Okay, so how can I simplify this? Okay, 1 over n to what power?
1/2.
Positive?
Yes.
Just kidding, just testing you. It's because I have it written like this on my paper. That's why. Yes, positive. April Fools, right? Okay, so you don't need it written like this just yet. It's just because I wrote it like that on my paper. But if we look at this comparison, we notice it's what type of series? It's a P series where P is equal to 1/2 and 1/2 is less than 1, which means this diverges. Okay, so then I go over to the other side and do the limit as n approaches infinity of n over the square root of n cubed plus n times the reciprocal, so n to the 1/2 over 1. Okay. So then I multiply across. This is the limit as n approaches infinity of n to the 3/2 power over the square root of n cubed plus n. That plus square root of n on the end is not going to do anything because we already have the square root of n cubed. And know that the square root of n cubed is the same as n to the 3/2 power. So those cancel out and we are left with 1. Is 1 positive? So we can say that the series diverges by limit comparison